Okay, let's unpack this. Today, we're diving deep into the world of Schröder numbers. Pretty fascinating stuff, named after the German mathematician Ernst Schröder. They're a really neat example of these, hidden patterns in mathematics we love to explore. So basically, these numbers, the main ones are called large Schröder numbers. They count specific ways to draw paths. Imagine you have an n by n grid, like graph paper, and you want to get from the bottom left corner, 0, 0, all the way up to the top right corner, and no n. Your steps can be 1 unit north, so 0, 1, 1 unit east, 1, 0, or one step diagonally northeast, 1, 1. But here's the key rule, the really important constraint. Your path cannot at any point go above the main diagonal line stretching from 0, 0 to n. And just to give you a feel for them, the first few are Sant naught is 1, then S1 is 2, S2 is 6, then 22, 90, 394, 1806. They grow pretty quickly.
Yes, and what's fascinating here is how such specific counting rules, for these grid paths lead to patterns that show up all over the place in combinatorics. It's almost like they're counting different aspects of the same fundamental structure. It's like a kind of mathematical DNA, which is why you see them pop up unexpectedly.
That's a really good way to put it, DNA. Okay, and that explains why they're not just about these specific lattice paths, right? So here's where it gets really interesting. Where else do these Schröder numbers make an appearance? What other structures do they count?
Well, one quite different area is in dividing up shapes,
Yes.
specifically rectangles. The Schröder number, nn, counts the number of ways you can slice up a rectangle into n plus 1 smaller rectangles using exactly n cuts.
Okay, n cuts for n plus 1 pieces. Makes sense.
Right, and these aren't just any random cuts. They have to be guillotine partitions.
Guillotine partitions, meaning?
Meaning each cut goes straight across the rectangle, either horizontally or vertically, from one side completely to the other. No partial cuts allowed.
I see, like a clean chop.
Exactly. Structurally different ways to do that. So, for example, if you want to divide a rectangle into 3 smaller ones, you need 2 cuts. And it turns out there are exactly 6 ways to do that with guillotine cuts. And S2, our second Schröder number after S0 and S1, is 6. It matches perfectly.
Wow, okay. From paths to cutting rectangles, that's quite a jump.
It is. And there's another definition, too, sometimes called Schröder paths. These are paths on a grid again, but they go from 0, 0 to 2 near, so they end back on the x-axis. The steps are different here. Northeast, 1, 1, southeast, 1, 1, and a sort of long east step, 2 units, right in one go. And the rule is similar. The path must never dip below the x-axis. Different geometry, different steps, but remarkably, the same sequence of numbers comes out.
That's amazing. The versatility is incredible. It really makes you wonder, how do these large Schröder numbers we've been talking about, how do they connect to other counting sequences? I think I've heard of little Schröder numbers. Are they related?
Ah, yes, that's an excellent point, a very important distinction. We have been focusing on the large Schröder numbers, Cn. There are indeed little Schröder numbers, often denoted as n. Sometimes they're called Schröder-Hipparchus numbers or even super-Catalan numbers.
Okay, so what's the difference between large and little?
It comes back to that main diagonal in the original path definition. The large Schröder numbers, S and n, count paths that are allowed to travel along the main diagonal using those one-to-one steps. The little Schröder numbers, S and n, count paths that can touch the main diagonal, but they're not allowed to have any steps that move along it. They have to immediately step away, either north or east.
I see. So large allows diagonal movement on the line, little only allows touching it.
Precisely. And there's a very simple relationship between them. For n greater than 0, the large Schröder number S and n is just double the little one, SN, so Sn is 2 SEON. Both sequences start with S0, 0, 0, 0, though.
Interesting. Simple relationship.
And yeah, you mentioned context. They definitely sit in a family with other path counting sequences. They're related to Dick paths, which maybe some listeners know those only use north and east steps and stay below the diagonal, and also Motzkin numbers, which allow north, east, and a level horizontal step, again with diagonal constraints. Schröder numbers sort of fit in that landscape.
Right, right. It paints a picture of variations on a theme. Paths with different allowed steps and constraints. Okay, so we've got grid paths, rectangle cutting, these alternative Schröder paths, connections to little Schröder numbers. But what's a truly, wow application, something really unexpected that ties things together?
Okay, well, this is where, for me, it gets really quite mind-bending. Schröder numbers have this astonishing connection to tiling problems, specifically tiling Aztec diamonds with dominoes.
Aztec diamonds, domino tilings. Okay, you have my attention. How does that work?
So imagine an Aztec diamond shape of order n. It's a particular diamond shape on a grid. And you want to cover it perfectly, no gaps, no overlaps, using just 1 by 2 dominoes. The number of ways you can possibly do this. It turns out to be the determinant of a specific matrix built from Schröder numbers.
A determinant, really. What's matrix?
It's called a Hankel matrix. It's a square matrix where the antidiagonals are constant. So you fill it with S1, S2, S3, and so on in a specific pattern. You construct this Hankel matrix using the large Schröder numbers, and its determinant gives you exactly the number of domino tilings for the Aztec diamond of order n.
That is unexpected. Is there a formula for that number of tilings?
There is, and it's beautifully simple. The number of ways to tile an Aztec diamond of order n is 2 to the power of n times, n plus 1 divided by 2. So 2 and n plus 1, 2.
Whoa. Let's try a small one for N1.
Okay, N1. The Hankel matrix is just the single entry S1, which is 2. The determinant is 2. And the formula gives 2, 1, 1 plus 1, 2 equals 2. A formula gives 2, 1, 1 plus 1, 2 plus 21 equals 21 equals 2. Matches perfectly.
Okay. How about N2?
For N and 2, the matrix is a 2 by 2. S1, S2, S2, S3. That's 2, 6, 6, 22. The determinant is 2, 22, 6, 6. Equals 44, 30, 36 equals 8.
And the formula?
The formula is 2, 2 plus 1, 2 plus 7, 2 equals 23 equals 8. Again, a perfect match.
That's incredible, truly incredible how a single sequence, these Schröder numbers, can connect grid walking, rectangle cutting, and something as seemingly different and visual as tiling Aztec diamonds. It really weaves things together.
It absolutely does, and it really makes you think, doesn't it? This raises an important question for all of us, really. How many other everyday arrangements or patterns, things we see all the time, might be hiding these kinds of complex mathematical structures just waiting to be discovered by you?